Okay, let's get started. So, welcome everyone to another lecture as part of our ID 5130 Parallel Scientific Computing course. Okay, so in the last lecture, we looked at motivation in terms of how the parallel processing parallel computing has evolved over the years. So in today's lecture, we will kind of still continue with chapter 1. We will look at quickly kind of retake a look at the motivation and see some interesting notes, some interesting facts. And then we will move on to classification of parallel computers. Okay, this is also known as the taxonomy of parallel computers. And finally, depending on the time, we will also look at how should we go about writing parallel programs. How should we go about writing parallel programs? Okay, so well, needless to say, you have to take notes just like in a regular class. All right. Okay, so in yesterday's lecture, we said that okay, the the processor performance has a kind of increased about, let's say, 50% per year, starting with about 1986 and all the way to 2002. That's what we said. Now, what is that something magical about 1986 that it has to, the processor performance has to increase at 50% per year compared to the previous year? So what is magical about 1986 was, this is the around the year about 1985 or 86 is when Intel launched its the famous 80386 processor that kind of relied on a new technology of processor fabrication, okay, which is known as a metal oxide semiconductor technology. Okay, so it's called a metal oxide semiconductor technology, or MOS technology, also later known as a complementary symmetric metal oxide semiconductor technology, also known as CMOS. Okay, so this is basically a type of a manufacturing process for field effect transistors that are used on the integrated circuits. This is basically kind of a manufacturing process or an engraving process for a kind of etching the transistors on the integrated circuits. Okay, so that kind of started off with around in 1985, which kind of led way to kind of putting or more and more processors or more and more transistors easily on the integrated circuits. Okay, so that started off with Intel 386 processor, and all these 50% increase per year, all these things kind of obey a law known as Moore's law. Okay, it's basically proposed by Gordon Moore, who was also the co-founder of Intel. So Moore's law is not a physical law, okay, like Newton's law. It's not a physical law. Rather, it's kind of an empirical law that is based on projection of or extrapolation of historical trends. Okay, so it's basically just a projection of historical trends that was observed and proposed by Moore. What it says is that basically it's kind of another statement of this increase of processor performance by 50% per year. And what it says is that the processor performance or the performance of the processors increases or doubles every n months. Okay, kind of doubles every n months. Now, this n is something that kind of kept changing depending on the number of transistors etched on the microprocessor. or on integrated circuits. The N initially started off around 1980s. It kind of started off saying about 12. That is, every year the performance would kind of double. Now, as we saw, the performance has kind of degraded 20% per year later on. So the N kind of course, has to increase to 18, and now it kind of settled around like around early 2000. It settled around like 24 or so. So that is kind of the Moore's law that which somehow kind of governs this increase in performance of the processors. Okay, so I mean, we of course saw that the performance of the CPU can be increased by increasing the kind of frequency of the transistors, right? Essentially, by putting in more and more transistors, you would increase the frequency, and then as a result, the CPU performance can increase. Of course, as you keep increasing this thing, you have problems with energy budget, because the power consumed will also increase as the frequency increases. As we saw yesterday, the power consumption also increases, right? And as a result, the energy budget, which takes care of essentially dissipating the heat safely and maintaining all the integrated circuits at a safe operating temperatures, would be a problem. As a result of this thing, at some point like early 2005s, the bigger microprocessors or bigger CPUs or cores were replaced with many small cores, right? Essentially to take care, and then that's where the parallelization has kind of began by the manufacturers. Okay, so now essentially, just to get an idea of just to put it on scale of what this kind of means, let us kind of look at the power density of the microprocessors. Okay, all right, so that's basically we are talking about now the power density. Let me write it here. Okay, power density is basically the energy consumed per, we would call it as meter cube. That means a Q dot here is basically either the heat that is dissipated or the power that is consumed, energy that is consumed, heat transfer rate. Okay, this is heat transfer rate per meter cube. Okay, so to state this slightly differently, we can also state this as what is the power consumed per meter square of this processor, of any processor or a system, and then we would like to call it what is this power consumed per unit area as you go along distance. That means per some quantity of meter. Okay, that means if you travel between 2 points, if you kind of measure what will be the heat dissipated by 2 locations, these could be, let's say, the separation between 2 transistors. Okay, or something like that. Okay, some kind of measure. That means if you're traveling on a particular integrated circuit, if you kind of separate 2 points, what will be the power density between these 2 points? That's what we're plotting. So on the x-axis we have, of course, meters is too big for process, so we use something known as micrometers. It's kind of quite small. And then on the y-axis we have something basically that is your Q dot by A. So that is basically your watts per meter square. Okay, that is the power. And then on the y-axis we will use a log scale just to put all these things in perspective. Let's say you have 10, 100 and 1000. So you have 10 watts per meter square, or sorry, let's put it centimeter square. Meter square is too big. So, and then 100 watts per centimeter square, and then let's say 1000 watts per centimeter square. And on the y-axis, on the x-axis, instead of going an increasing value in this thing, I would the distance between the 2 nodes or 2 transistors is kind of made to decrease. Okay, so this is kind of a reverse axis. So I start off with, let's say, about 1.5 micrometers, and then I go all the way to about 20 times smaller, that is 0.075 micrometers. Okay, so that is kind of very small. And then in between you have some points which I would like to mark here because they are prominent. These are 0.25 micrometers and 0.15 micrometers. Okay, so we have these two, and then we can of course kind of draw a line. Okay, so the line is basically some line that goes like this. Okay, now if you look at what will be the power consumed or power dissipated by the Intel 386 processor, the early on in around, let's say, in 1986 or something, they were about kind of falling in this range, because the distance between them is also large in terms of, I mean, this 1.5 micrometer is small, but then it is kind of large when compared to today's distance between the transistors. Okay, so the Intel 386 kind of processor somewhere lies along this line, and 486 is here. So this is E386, this is I486, and so on. And then as new and new processors kind of kept coming in, by putting in more and more transistors, this distance between the transistors kind of decreased. So we kind of went in this way, and the power, of course, consumed increased, because they are now operating at a higher frequency. As a result, they would require more power to operate at higher frequency. Okay, that means now we have then the Intel Pentium 3, Pentium 4, Pentium 1, all those things were somewhere lying here. Okay, so let's say this is P1, this is Pentium 2, this is Pentium 3, and then around Pentium 4, and so on. So all of these kind of lie somewhere around this range. Okay, so this is the range where all these things kind of lie. Okay, about this gap. All right, and then so as you can see, there is an increase in the power consumption as you decrease the distance between the transistors. That means if you pack more and more transistors in there. Okay, all right, then if to put in perspective, let us see where will we stand if you, in terms of power consumption, if you kept increasing. This should be kind of lies a little bit below 100 watts per centimeter square. Okay, of course you have the new process which are all lie somewhere here. Okay, now to put in perspective, what will be the corresponding power density when you compare, let's say, a microprocessor with other systems that you know, right? So that we can get a scale or a feel for what is the amount of heat that these guys will dissipate. Okay, so of course the other systems you know are, let's say, a nuclear power plant. Okay, if we have a nuclear power plant, of course the distance between, or the power density, is much smaller than if I kind of put it on this scale. The nuclear power plant would be somewhere here. Okay, around 800 or so, 900. So this would be a nuclear power plant. Okay, that's a nuclear power plant somewhere here, which is operating. So if you keep going on this scale, and then if you keep increasing this, then you get to a rocket, right, which is also has a lot more power density, right? And if you keep increasing on this thing, of course you cannot with your process, where would you reach? You would reach, of course, the hottest element, that is hottest object, that's your sun, right? Okay, surface of the sun. Okay, that's kind of to put in perspective where we stand with our heating capacities of the process with respect to other physical things that we know. All right. Okay, so that kind of is good. So that's kind of some kind of motivation for the study, and you can also get we can also get some more insights into what has happened, or into the evolution of parallel computers, by looking at the frequency of the CPUs, okay, or the cores, as well as the number of floating point operations that the processors can perform. Okay, so essentially, as a user, you are only interested in how many floating point operations that a CPU can perform. These are called FLOPS, FLOPS. Okay, and the frequency of the CPU or the core is the base frequency of the core we are talking about, of the processor. Okay. Now, well, what does this got to do with parallel computing? We will see that soon. So one of the things is, let's say if you look back in 1986, and we kind of tabulate here. Let's say we tabulate the frequency of the CPU or the core, as well as the flops. Okay, so if you back in 1986, if you look at the fastest supercomputers, then the frequency of the core or the CPU were kind of around 100 megahertz. Okay, whereas the number of floating point operations they can perform were about approximately 100 mega flops. Okay. Now, what about it now? What is the fastest supercomputer that we know now, or we have? Well, there are many computers, many supercomputers, which are also known as clusters. Okay, a list of the top supercomputers is maintained at top500.org. I encourage you to look up this website and see who is the topmost supercomputer or which country, and then other things as well. You will also figure out where India stands, around 80 or something like that. So the Fugaku, I think, is the fastest supercomputer, and it's kind of housed in Riken Center for Computation Studies, that is in Japan. Okay, and it has around 7 million cores or CPUs. That's quite a lot. Okay, it kind of consumes 30 megawatt of power. This is quite a lot of power. Like, to put in perspective, what will be the percentage of this compared to the power consumed by Chennai city? I think that we can easily look up. That is quite significant, right? So okay, so it consumes 30 megawatt of power, and it has 7 million cores, and it can also do approximately about 4 into 10 power 9 megaflops. Okay, or essentially it is 400 into 10 power 3 teraflops. Okay, so that basically around 4 into 10 power 9 megaflops is what we can write it. Okay, and then what will be the frequency of the processors that it is using? The frequency is only 2.2 gigahertz. Now this is nothing great, right? For example, if you take your a good standard laptop or a desktop would have a similar frequency as well. Now, of course, the number of floating point operations it can perform is quite large compared to what your desktop can perform. Okay, so this is of the order of 10 power 9. So if we compare, the idea is now I would like to see over these 1986 to 2020. Okay, so this data is coming from, let's say, about November or December 2020. We would like to see how does this frequency increased over the over this 34-40 years of period compared to how many flops have increased over this period of 40 years. Okay, approximately. That means this one has increased by 2.2 into 10 power 3 megahertz divided by 100 megahertz, right? That basically gives you around, this is 22 into 100 is of the order of 22, that is of the order of 10. So basically the clock speed, right, or the frequency of the core or the CPU has kind of increased by tenfold. That's okay. Then what about the number of floating point operations it can perform? That has increased by 4 into 10 power 9 megaflops by 100, right? This is quite large. This is of the order of 10 to the 7, which is very large, right? So that means what we see is that the basic the speed of the basic electronic components basic electronic components has increased only a tenfold, whereas the performance, the number of floating point operations has increased by of the order of 10 power 7 over the 3 decades or 4 decades, right? That is quite dramatic change, dramatic increase, or right? And how did this happen? This happened because of the answer to this lies in parallel processing, right? So we are talking about so many cores, right? That's why this has kind of happened. Okay, to kind of quote Michio Kaku in his book, The Future of the Physics, he says that today, your mobile or the smartphone that you have in your hands is more powerful than the entire National Aeronautics and Space Administration of USA, the entire NASA offices, or all the computing power put together back in 1969, when they placed Neil Armstrong and Edwin Aldrin on the moon, right? So the entire computational power they have back in 1969 is so small that the mobile you are holding it right now is much more powerful than the entire computation facilities they have when they put 2 astronauts on the surface of the moon. Okay, that is kind of quite tremendous, and the answer to this lies in increase in the parallel processor technology. Okay. All right. Okay, so that kind of is probably, I hope is the enough motivation to pursue this course, and we will move on to the next topic, that is basically the classification of parallel computers. Okay. So the best known classification of parallel computers is known as the Flynn's taxonomy. Okay, so in Flynn's taxonomy, we are kind of looking at two things. One is known as the instruction stream. The other is known as the data stream. Okay, what we mean by instruction stream is basically the set of instructions that we have to give. For example, you have to add something, you have to subtract something from something else, you have to multiply, you have to divide, and you have to do a lot more operations. So this basically is the instructions or the operations. And the data stream is the data that you have. You have 2, 25, 50, 18, and so on, right? So you have some data. So that is your data stream. Now, in Flynn's taxonomy, what we are looking at the multiplicity of the hardware that we have that can basically handle the instruction streams as well as the data stream. Okay, that means we are looking at do we have a, when we say multiplicity, we are looking at do we have a single one or do we have a multiple one. Okay, for both the instruction stream and the data stream. That means if I write let's say instruction, write it better, instruction stream, you can have a single instruction stream or you can have a multiple instruction stream. Okay, on the x-axis, and on the y-axis we have data stream. Now the data stream can be a single data stream or a multiple data stream. Now this leads to, of course, 4 configurations, because you can have a single instruction stream, single data stream, multiple instruction stream, single data stream, and you can have single instruction stream, multiple data stream, and multiple instruction stream and multiple data stream. Okay, so that is basically the 4 configurations. We call it as single instruction stream and single data stream. That is called SISD type of architecture. And then multiple instruction, single data stream, and then you have single instruction, multiple data stream, and then you have multiple instruction stream and multiple data stream. Okay, so we have these 4 categories of parallel computers according to Flynn's taxonomy of classification, which is kind of the most, or the kind of the best classification that exists in the literature. Okay, so let us quickly see what does these configurations mean or classifications mean, and how do we relate our existing or obsolete computers according to this classification. So the first one is known as the single instruction stream, single data stream, or SISD architecture or configuration. So in this one, of course, there is a single instruction that is basically is applied on a single data at a time. Okay, so these basically is a characteristic of single processor or uniprocessor architectures, okay, which are now kind of obsolete, because even if you buy a small desktop computer, it kind of comes with multiple cores. So a uniprocessor architecture is something known as a single instruction stream, single data stream architecture. Okay, and the second one is basically single instruction stream, multiple data stream. That means we want to do only one operation on a set of data. Okay, that means we have a set of data which is, let's say, kind of a vector like this, and then we want to divide this vector into several parts, and each of the parts will be dealt with different process. For example, this data will be doing one operation, and then the same operation will be done on the next data, and also on the next data, and so on. Okay, so that means we have some data, so we have multiple data which we are going to kind of split, but we are going to do the same operation on all of them. So that's why it is single instruction stream and multiple data stream. So this is a characteristic of vector processors. okay, which existed a decade back, and I think few more are still there. That means these perform so the multiple process would perform basically the single instruction on all the data that we have. That means they have to just do the same operation. Another example of a single instruction multiple data in some sense is basically your graphic processing units. Okay, so if you consider a graphic processing unit, you have graphics processing unit or GPU, in which essentially you have a several graphic elements. For example, you have a point, you have a line, you have a triangle, or you have a quadrilateral, all these things which you have to kind of somehow represent them, and then eventually you have to draw all these things on a computer monitor using let's say some pixels. Okay, so you have pixel of data, so you have to kind of highlight these pixels by translating all these points, lines and triangles into this one. So this kind of translation is only few lines of C code or something, but the same set of operations have to be performed for all these elements. Okay, now these elements can be very large in number, right, depending on the surface you're trying to visualize on the screen. That means we have to perform the same operation of a few lines of C code for all these elements, different elements, and such that you can kind of display them on this thing. Okay, so that is what is done by graphic processing units, whether you're playing a game or whether you're just watching a movie or just looking at some good image or something like that. Okay, so this is where they can actually have several processors, I mean essentially several data being done by using optimization. Okay, that's what is kind of done by GPUs. So so this is another example of a single instruction multiple data, but GPUs are kind of approximately, we can call it as SAMD systems, because GPUs are not in a true sense SAMD systems, because most of the GPUs actually come with dozens and dozens of cores of themselves, which can actually can perform multiple instructions as well. Okay, but in some sense we can probably call GPUs as single instruction multiple data machines. Okay, so nowadays, as we see in this course, GPUs are becoming very popular for high performance computing. Okay, and as a result, several languages are developed. One of them is CUDA, the other one is OpenACC, and so on. And we're going to learn OpenACC later on in this course. Okay, let's move on to the third classification, that is your multiple instruction stream and single data stream. Okay, that means we have multiple instructions but single data. Now this is something that was not very common in the parallel scientific community, and only very few commercial systems were built that kind of rely on multiple instruction single data kind of architecture. Okay, so some of the examples are kind of targeted at specific applications such as digital signal processing and so on, but these are not very they were not very successful architecture as such. So Flynn kind of suggests that because of the lack of a natural mapping from, let's say, the programming constructs to the MISD kind of organization or architecture. So because of this lack of such natural mapping, MISD systems were kind of restrained in their development, and then did not kind of find a kind of a good market value or a commercial value, and that's why their development was not kind of much at all in the commercial or the parallel computing community. Okay, so that is about the multiple instruction single data stream. And finally we have this multiple instruction multiple data stream, that is the fourth one, in which we have multiple instructions. That means we have multiple cores which are essentially manipulating multiple data. That means we have several data, a lot of data, which is being manipulated using multiple instructions. Okay. Now, multiple instruction, multiple data is the most generic classification that you can get, or category you can get in parallel computers. And MIMD systems again can be thought of as two classifications. The first one, so essentially the MIMD systems usually are kind of have fully independent CPUs. They have fully independent CPUs or cores. Okay, and these can be thought of as either a shared memory systems or distributed memory systems. Okay, so these are so in the first classification, in the shared memory kind of systems, we have, I mean, the independent or cores or CPUs are always there. In the shared memory systems, all these cores can access, they basically have a RAM or a memory which can be accessed by all the cores. Okay, that is a shared memory system. Whereas in the distributed memory systems, each of the cores have their own memory or their own RAM. Okay, which cannot be accessed by the other cores. Okay, so in the shared memory kind of architecture, do better here. Okay, shared memory architecture, we have basically several CPUs. Okay, these are several CPUs, and they're all connected through some bus or an interconnect. So let's say this is a bus or an interconnect. Okay, these are all the core 1, core 2, and so on. These are all the cores, and they're all connected through a bus or interconnect through a single memory, or even if they have multiple memories, they all can be accessed by all of them. So this is the memory they have, okay, which can be accessed by all of them. Now, within the shared memory, again, depending on how the memory is accessed, there is another classification known as uniform memory access as well as non-uniform memory access, but we are not going into those details at the moment. But you can kind of learn if you are interested on how depending on how fast or easy it is for a particular core to access memory coming from the other core, is how the uniformity is kind of defined. Okay, now we'll come to the distributed memory systems. So in the distributed memory systems, each core has its own memory. That means you have a core or a CPU. It has its own memory, and then similarly we have another core or a CPU, and it has its own memory, and so on. Okay, so we have several cores, and then each has its own memory. Now, of course, all these are, again, the cores are all again connected through some kind of interconnect to transfer data. Okay, so this is again an interconnect. Okay, and but then this memory is kind of only accessible by this core. Okay, so the other core from here cannot access this memory directly. Okay, if you want to access, it has to be kind of you have to use kind of some kind of send receive kind of packages or communications. All right, so that is about distributed memory systems. Now, in the distributed memory systems, you also have, I mean, this can be thought of as your regular commodity PCs, your regular personal computers. They are all connected using, let's say, Ethernet or something like that. Okay, of course, this will be very crude distributed memory system because it will be slow. In general, you would have something known as nodes, okay, which are independent CPUs or cores, which are connected through high-speed switches, okay, such as gigabit switches and so on, and these are known as clusters. Of course, you can also build your own crude clusters using by kind of connecting several PCs and things like that. Okay, so in general, these nodes themselves will have multiple cores. Okay, so as a whole, we may see this cluster as a distributed memory system. However, within each node there will be multiple cores, so these are basically, each of the independent units would be kind of standing as a standalone shared memory systems. Okay, that means we have both these technologies in here. That's why most of the clusters usually are called as hybrid systems, because they make use of both the distributed memory as well as the shared memory in one go. Okay, so all these top 500.org clusters that are listed there, and many other supercomputers that we have, they are all kind of fall into this MIMD, or the distributed memory, or the hybrid system technology. Okay, so in this course, of course, we are going to learn OpenMP, which is basically an application for shared memory systems, and we're going to learn a message passing interface, that is MPI, which is basically for distributed memory systems, and you're going to learn OpenACC, that is for running your jobs on graphic processing units. Okay, fine. So that is the three main things we're going to learn in this particular course. So that is kind of completes the Flynn's taxonomy, or the classification of computers. Now let us also quickly look at the third thing we want to discuss today, that is how do we go about writing parallel programs. Okay, writing parallel programs. Now there are, of course, the writing parallel programs. How do we go about them is kind of dictated by the corresponding architecture that we are kind of dealing with. Now we have convinced ourselves yesterday that we must write parallel programs, isn't it? We must write parallel programs. Now once we have decided that, convinced that we must write parallel programs, we have to now see how should we go about writing them. And this is kind of a general introduction to this. So most of the parallel programs kind of rely on the idea of partitioning the work, right? I think this is obvious. If you have, let's say, 10 people working on the job, you can actually probably get it quicker depending on the type of the job and the type of the work accomplished. So as a result, partitioning of the work is the main principle of writing a parallel program. Now partitioning of the work can be done broadly in two different ways. One is known as task parallelism. The other one is known as data parallelism. Okay, so as the name suggests, in the task parallelism, we are basically going to parallelize the different tasks. Okay, so in the data parallelism, we are basically going to split the data among all the cores such that each core would perform pretty much the same operations, right? Just like what we saw in the context of a GPU. I mean, they all perform pretty much the same operations on the data, whereas the data itself is kind of split among the cores such that it kind of is a data parallelism. Okay, let us see a couple of examples of task parallelism, or let us see an example for each of these task and data parallelism so that we can understand better. So let us consider an example. So we have for this course, let's say we have 100 students. We are not yet there, but let's say we assume we have 100 students, and then we have 5 teaching assistants, and we are you have just, let's say, submitted your assignment 1 that contains, let's say, 5 questions. Okay, and each of the question is different. And these have to be graded. Let's say the TAs would grade them. So essentially grading one particular question is one task, right? That means if let's say the teaching assistant 1 grades the question 1 for all the 100 students. Okay, now let's say question 1 is very different from question 2. Question 2 is something different, and TA2 would kind of grade the question 2 for all the 100 students. So essentially we are dividing it into different tasks and giving it to different cores or different processes, right? So teaching assistant 5 will grade question 5 for all the 100 students. And here essentially the disparity comes in having that the question 1 is different from question 2 is different. These are all different. Okay, for example, this can be a question on, let's say, OpenMP. The other one is a question on matrix multiplication using serial code and things like that. Okay, that is about task parallelism. Now what about the data parallelism? Now we can use the same example to discuss about data parallelism. Instead of each TA grading one question for all the students, Each TA can also, the TAs can also split the papers, right? They can also distribute that. Each TA would get, let's say TA1 would get 20 answer books, okay, and TA2 would get another 20 books, right? They would get TA2 and so on, such that everybody gets, each of them would get 20 answer sheets, okay? So TA5 also gets 20 answer books, but then now TA1 has to grade all the questions, question 1, question 2, all the way to question 5 for only for 20 students, okay? That means TA1 would be doing the same job as what TA2 would be doing. That means TA5 also would be doing the same set of instructions. They will be executing the same set of instructions, right? That means the instructions are the same. Only thing is the data is now, or the data that we have, that is 100 students, is now split into piles of 20, right? Okay, so this is basically your example of your data parallelism. Okay. Now, in general, if you write a parallel program, it would consist of both task parallelism and data parallelism, and we will see how. For example, let's say if you recall, we had in the last lecture we looked at this global sum example, right? So so one way to accomplish global sum is that all the cores would send their data to the master core, right? Now before they send the data, they all have to perform some operation. That means they have to sum their own data, right? Now summing their own data from the values, essentially calculate the value, right, and then sum them, right, equal to sum x. Now this step is basically what is known as your data parallelism, right? Essentially they are performing the same operations, all the cores are performing the same operations with their own data, right? So this is basically the data parallelism because the instruction set is the same. Whereas after they are done calculating the data, what they have to do is they have to, for example, if it is any core, they have to send data to master core, right? Whereas if it is a master core, it has to receive the data and then sum the received partial data, right, or partial sums to calculate the global sum. So this can be thought of as a task parallelism, right? Because now the task is different depending on whether you are a any other core or you are a master core, right? So this can be thought of as a task parallelism. All right. So that is about an example. In general, you would kind of have both task parallelism and data parallelism depending on the algorithms and the things you are working with. All right, but this kind of will help you visualize what is what. Now let us also look at three kind of keywords that we encounter in parallel processing. In order to do that, let us look at, so essentially all these things, or writing parallel programs would be very easy if, okay, so writing parallel programs would be easy if all the cores, if the cores or the processors can work independently. That means they don't have to talk to each other at all. Okay, if they can work independently, there is no need for a communication, then essentially writing parallel programs is a piece of cake, right? Because it's essentially it means that it is exactly the same as writing a serial code. Only thing is that you just have to distribute the data to each of the cores. Unfortunately, life is not so simple, so as a result, we need communication between the cores. Okay, as a result, this will lead to a lot more complexity. Okay. For example, if you look at the yesterday's example of global sum calculation, we had an alternative way, right? An alternative way where each of the cores need not send it to the master core, rather they would kind of send it to their other core, and then we had this kind of a log p to the base 2 kind of approach, where basically we have a tree structure in which the communication has to be sent. Right? Now this is very easy when you plot it as a tree structure, but it becomes a lot more complex when you have to write the real code for this. Okay, which we will see later on when we learn about MPI and things like that. Okay, so this all happens because of the coordination or the communication, that is kind of coordination required between the cores. Okay, so coming to the coordination, we can kind of talk about three ways of coordination. The first one is, of course, communication is one coordination that is required between the cores. So essentially they have to communicate their own partial sums to the master core so that the global sum can be found. Okay, the other coordination is known as load balancing. So as we see, we would like to assign approximately the same number of elements. For example, in the yesterday's example, we would like to assign 3 elements to each of the cores or something like that, such that every core would be getting equal amount of work. That means all the cores would be getting equal amount of work and they all finish approximately at the same time. Okay, such that we are not wasting any other computer power. Okay, so that is known as load balancing, which is also a type of coordination. Load balancing meaning we would like to load each of the cores approximately uniformly. So we want to balance the load on the core such that we are not wasting any computational time. Okay, the other coordination that needs to be kind of accomplished in any parallel program is known as synchronization. Now synchronization is also a type of coordination where for example, let's say if the master core has to distribute these data to all the individual cores, then all the cores have to wait until the master core has got all this data to them. They should not race ahead and start calculating whatever is the initial zero values or random values that they have. Rather, they all should wait until the master core has given them the data. So it means they have to have some kind of a synchronization point where they will all wait until, or at least they will wait until the master core has sent them the data to them. Okay, so that is known as synchronization. Now they need not wait until the master core send it to all the cores, but at least they should wait until they got their data. Okay, so that is known as synchronization, and this also can be accomplished by using some functions where until all the cores have entered that particular function, they will not proceed further. Okay, so these kind of coordination tasks is what basically makes writing parallel programs a lot more complicated than it can be. Okay, so most of the parallel programs are written using explicit parallel constructs, okay, or constructs, or that means we would write explicit statements in which how do we handle a particular loop or how do we send the data, all those things, and they are written as extensions to languages such as C, C++, or Fortran, or even others. Okay, but we would like to kind of stick to these things, so it's kind of is not very difficult if you want to do it for another programming language. Okay, now in case if you have not started or if you don't have a preference for working with C or something, I would suggest you to work with Fortran, because this is as simple as or even simpler than C. Okay, and most of the scientific codes are also written in Fortran. Okay, so which will make your life much more simple. Alright, so we will learn about all these things in the coming lectures. For now I'm going to stop here. So this kind of finishes the chapter on introduction. In the next lecture we will move on to the OpenMP programming model. Okay, alright, thank you. Talk to you in the next class.